Hi, my name is Dylan.
My name's Tyler.
My name is Will, and this is our cargo cafe design.
For our building, we decided to design a small single-purpose cafe and study location.
Since our cafe will be completely constructed from cargo containers, the exterior will have a uniform appearance.
Our main design goals are based around sustainability as well as feasibility of the integration of energy-efficient design strategies.
Here are a couple photos of our finished floor plan and roof plan. Our first goal for sustainable design was to get at least LEED Gold certified, since the LEED rating system is a widely accepted and reputable standard for sustainability in the US.
Our highest LEED point values came from the category of energy and atmosphere, with 18 out of 33 available points. To meet this goal, we needed to minimize annual energy usage through systems such as HVAC, refrigeration, and water heating. We can reduce the annual energy consumption through energy-efficient systems and renewable energy sources. Working with power companies such as Xcel Energy, we can reduce our total energy waste.
Second highest category of points that we are striving for is indoor environmental air quality. Within this category, we are aiming to achieve all 15 out of 15 points. This includes maximizing thermal comfort as well as supplementing electrical indoor lighting with natural lighting. We are also picking materials that will not emit carcinogenic VOCs, which fulfills the category of low-emitting materials for indoor construction.
3 new shipping containers would cost about $8,000 per unit, totaling $24,000 for our project. However, using repurposed shipping containers, it will only cost us $5,000 per container, saving us money and reducing pollution.
In terms of construction costs, we used estimates based off of currently existing small restaurants in DC. Overall, the construction cost would total about $200,000 at $200 per square foot. In terms of operation costs, the total would be around $10,000 a month, including employee salaries, food and beverage costs, utilities, and insurance.
Our building will have 100 square feet of PV, with an estimated cost of $10,000. This initial investment will have a payback period of 4.7 years, which is well below the desired 7-year window. As for the HVAC system, the unit itself will cost just under $3,000 and will be talked about later.
We use Climate Consultant to get estimates on the best passive design strategies for each season. We will be discussing different strategies for each season since the design conditions change. In January, our passive design strategies will be passive solar and wind protection. For wind protection, our cafe includes a south vestibule with a second set of doors so wind can't directly blow into the building and cause discomfort to our occupants. This is perfect because in January in DC, the wind blows from 330 degrees, which is to the south. These two strategies together afford us a total of 85 hours of thermal comfort throughout the month of January.
In the spring and fall, where temperatures tend to fluctuate between cool and warm, passive design strategies recommended by Climate Consultant are passive solar and sun shading. Using these strategies, more than 250 hours of thermal comfort can be achieved in April and about 200 in October.
Using both sun path analysis and energy calculations, we have determined that the best orientation for our cafe is facing south. This allows for passive solar, daylighting, and natural ventilation. We have implemented a 2-foot overhang on our southern-facing wall. This, paired with a 40% window-to-wall ratio, will result in the most energy-efficient southern-facing envelope design. Here are some renderings that show the sun shading for summer and winter months. In the winter rendering, it is clear that the low sun angle allows for passive solar through the southern-facing windows. In the summer, the 2-foot overhang shades the windows, reducing our overall solar radiation.
To design the most efficient building envelope, our values as well as thermal massing must be considered due to Washington, D.C.'s climate. Final envelope design for exterior walls consists of 4 layers: exterior metal shipping container, insulating board, vapor barrier, and 8-inch CMU with insulation and cells without reinforcement. With these components, the total R value is 34.5, and we calculated a heat loss of 610 BTU per hour for winter and heat gain of 55.4 BTU per hour for summer through the walls.
We chose these materials not only for their insulative properties, but also for their thermal capacities. The reason we chose to use CMU block was for its thermal massing. This allows us to store heat over time so that it can be released into our building as the outdoor temperatures decrease. This passive design strategy will have a massive impact on our heat gain through the warmer months. Our choice of envelope also meets all ASHRAE envelope requirements from 90.1. We will see a total heat loss through our building of 3,524 BTU per hour in the summer and a total heat gain of 370 BTU per hour in the winter.
Using the ASHRAE handbook, we were able to estimate infiltration through our entrance as 2 ACH with a 50 square foot vestibule. Using vapor barriers, a high quality building ramp will be chosen. This will allow the least infiltration through the building envelope. For ventilation, ASHRAE recommends a value of 7.5 CFM per person for indoor ventilation. A predicted maximum of 20 occupants, we expect 150 CFM of ventilation throughout the space. We supplemented this using natural ventilation to the controllable open windows at the top of our cafe. These windows can be opened during hot months to allow hot air to escape to the top portion.
Besides just using the basic Excel tool to get R values for all of our envelope components, we created a more advanced iteration of this tool that lets us analyze the heat transfer through our envelope, including windows, and getting a more comprehensive R value using parallel series calculations. We also included heat transfer due to radiation through the windows. This results in a heat loss of about 3,000 B2 per hour in the winter and a heat gain of about 11,000 B2 per hour in the summer.
Our final iteration of the heat transfer Excel design tool not only accounted for radiation in windows, but also heat giving off by occupants, electrical lighting, coffee making equipment. We found that in the summer, cooling load is 21,000 BTU per hour. In the winter, the heating load is 3,000 BTU per hour. This is due to radiation to the windows, which significantly decreases our heating load by 4,500 BTU per hour.
Along with this, our cooling load estimates can also be reduced. This is due to our 2-foot overhang as well as the remote-controlled sun shading for our skylights. It is estimated that with these two additions, we will be able to decrease our cooling load by about 5,700 BTU per hour.
To handle our heating and cooling loads, we need to find one system that can manage both. We ultimately chose the 27,000 BTU mini split air conditioner heat pump. This system costs just under $3,000 and is expected to be able to handle loads of 27,000 BTU per hour for heating and cooling loads. It also comes with 3 indoor units that we can place where necessary for multi-zone control of the space.
To summarize, we want to reiterate our most crucial strategies that allowed us to reach our design goals. Our cafe has skylights with controllable shading in order to have passive solar in the winter and decrease cooling load in the summer. We included a 2-foot overhang on our cafe's south wall to also help with keeping the cafe warm in the winter and cool in the summer. The south vestibule we included in the design keeps wind from blowing directly into the building, increasing both thermal comfort and decreasing heating loads. The windows on either side of the building can open in the summertime to allow natural ventilation and cooling to occur. Solar panels on our roof contribute to decreasing usage of grid electricity, which lessens the load our cafe has on the environment.
We believe we have achieved an optimal design to minimize our impact on the environment and promote sustainability. Because these strategies were so effectively incorporated into our building, we believe we have achieved our goal of integrating an energy-efficient building design.
Thank you.